Thank you, everyone. So I'm going to talk about Ubuntu Touch and what is going on with snaps at the moment. Yeah, I was introduced already, so I'm going to skip that part. If there are some specific phrases or words or whatever descriptions that are coming up during the slides that don't make sense at that moment, they will most probably be explained later. Things like Halium, libhybris, what they are, etc. So the agenda is here, Ubuntu Touch architecture. We go through this because my goal is actually to explain what is going on with the snap support on Android-based devices specifically and what is making it so hard. The hurdles across the board from early boot, from the kernel to early boot to running on user-space side. We're going to see some libhybris involvement, what's changed in snapd, integration changes for Ubuntu Touch specifically, and what to do about a potential, in the future, all-snap deal, and how to pull that off, actually. So we have 4 particular things that we want to cover for the architecture here. We have the kernel, we have early boot, we have the rootfs, and something that might not ring a bell right now, that is Halium. For Ubuntu Touch specifically, we have 2 modes of operation, usually. We have mainline-based devices, which pretty much are similar to what you're used to from a regular desktop environment, running on a laptop, desktop, whatever, mainline system with Mesa, and minus the phone parts, which we have to maintain, of course. Those things are already working pretty much out of the box if the kernel has the support for it. On the other hand, though, we have something called Halium. Halium is a little bit of an abstraction here and hardware support enablement work that allows us to reuse Android vendor blobs, drivers, and HALs for driving the hardware, connecting it to a regular GNU/Linux system. And it also means that we're relying on Android vendor kernels, usually. So, ding dong, we have something here that has grown over the years, coming from the Android and Google side of things. So we also have generational fragmentation. And that includes things happening in the kernel space, for example, graphics and memory allocation for putting things on the screen. Out-of-memory killer, which used to be available in Android up until 9, to be the default, actually, up until Android 9, which still has some bits and pieces in there which you can re-enable in the kernel, but yeah. Then there's also userspace for Android that we rely on, interfaces to the kernel APIs that try to abstract it away to make it reusable across the different generations, but also the binderization of HALs, of the hardware abstraction layers. And the binderization, I will get into what binder is later. Binder is one particular important piece. There's also the Initramfs, an early boot situation, which is completely different on pretty much every device that you find out there. And also the introduction of AB boot slots in Android itself and bootloaders providing that functionality. So, what do we have as requirements for supporting snaps on Ubuntu Touch? So we need AppArmor. What we usually do is we take downstream patches from a similar LTS patch set or apply patches of the upstream AppArmor GitLab and apply those on the vendor kernels themselves. So either it's a replace thing or patching on top. And we are still trying to do some things here to make it work, integrate it properly, to make the compile, to make it really work. Also add some patches on top because Ubuntu Touch has a few things that just 1 or 2 patches that are required for thumbnails to work properly, not anymore, but other components. And also enabling namespaces and other various kernel features that are required to actually drive the Halium libc container that we have. We also need config-vt and config-sys-vipc, which are not enabled by default in the Android vendor kernels. And there's also something with keeping the kernel ABI stable. And for that, I have a different set of slides here. Google introduced something called generic kernel images, which they're actively working on. And that means having 1 kernel for a various set of range of devices. 1 kernel build running everywhere. That's their goal. And that means that Android vendors who want to ship Android, they must follow. And also, there are some kernel modifications inside of the upstream Linux kernel, or on top of the Linux kernel, that make it possible to actually achieve this. It's like making struct sizes always the same and adding some padding on top. And here we have a few examples. Here we have something with the sysv IPC ABI compatibility, where we comment out, actually I think this was done by Nikita over there. We simply just comment out the places where it used to be and move them using those new Android kernel ABI use and replace and reserve macros, which basically ensures that the structures in the kernel are always the same size and that they're padded properly, and we are moving things around so that the modules, the kernel modules, the actual drivers that are actually in use and shipped by the vendor, so that we can reuse them, because there are a lot of kernel modules in a phone nowadays which make it like hard to compile it yourself. There is another one with POSIX-MQ, similar situation. We have the kernel ABI use instead of a reserve here. And also what we have to do for C group v2 and eBPF is allow the capability sysadmin to allow changes on the BPF side of things, because otherwise snapd or installing Docker, for example, wouldn't have the device C groups working properly, because snapd can't just provide an eBPF program to check for the permissions. Now, Bootup, early boot and Initramfs. We're going to go through 3 different types of Bootup. We have Initramfs tools Halium, which is similar to what people working on Ubuntu Core or Ubuntu Touch are used to. It's a Debian environment which sets up the Android superpartition, which sets up the system and the writable user data partition. It mounts some of the bind mounts for writable paths on top of the read-only system. And it looks very similar to what Ubuntu Core used to look like from the Initramfs perspective. Reason? It looks like a regular GNU/Linux Bootup environment. Then there is Initramfs less, something that I came up with because of the Pixel 3a. It is basically copy-pasting the code from the Initramfs tools Halium and putting it in /init in the system, which then gets used during early boot. Does similar things. It mounts the writable paths, some of the writable paths, sets those things up, and chain loads systemd afterwards. The reason? Google made the recovery partition optional in Android 9. So the Initramfs part of the kernel image is actually being used for the recovery, and based on a command line flag, it actually either boots into the system or into the Initramfs. And now we have another one. We have concatenated Initramfs because Android and Google. Google reintroduced recovery partitions and actually a bunch of other things, and that ships Initramfs in different partitions, which then get concatenated by the bootloader, passed to the kernel. The Halium Initramfs is one of those. Also the others with different partitions containing the kernel modules by the vendor, they're also part of that, and they get loaded in this early boot environment. And also something important in early boot is the super partition. Android 10 introduced something like an LVM-style volume container, which got its own custom header format. So we need something to make that usable with LVM. But Parse Android DynParts solves that issue. It basically provides all the necessary info for LVM to set up all the volumes there. And it contains also vendor blobs in various other volumes. And it is also an A-B system. So either A or B, depending on what the bootloader tells the kernel to have mounted. Then we come to the root of us. We have Ubuntu as a base, which is what you're used to from Ubuntu ARM64, IMD 64, or ARMHF. It's got systemd, it's got all the typical Ubuntu userspace libraries and services. But we also have something called libc Android config, which mounts the rest of the partitions that are supposed to be mounted, sets up the remaining writable paths, and it initializes the Halium libc container with optional configurations for PulseAudio, for other things provided by the port maintainer, by the systems integrator. And yeah. So we have additional services on top of that. We have Mir, as used by Lamiri, for handling displays and input. We have some integration services like Ophono, SensorFW, and HFD service, and additional daemons for providing functionality in UX services like online accounts, download manager, etc. Those are not particularly accessible from Snap right now, but they could be and they will be in some way, shape, or form. So what is Halium? This is another part which makes the all-Snap situation very hard to pull off. We have a stripped-down Android version, which is just getting rid of all the Java bits, running it in a libc container, starts Android/init and its HAL services, and just enough for hardware enablement to run. This means that we have sort of like these user-space services which talk to the kernel in a confined environment, sort of like a confined environment. And we talk to it either using sockets in some cases, or most importantly through binder, which is the IPC mechanism of Android, which I'm going to get into later. Also important for the Halium story is we have generic system images. So Project Treble by Google for Android introduced the concept of a separate partition, where we, as UBports or the community, don't ship the blobs anymore, but we rely on the vendor blobs that are part of the vendor-provided system. It's in a separate partition. We don't wipe that. What we do wipe is the system partition, and we put our rootfs there with a generic system image that is one binary for /system from the Android perspective, and that works across a multitude of different devices. So that modifications are not built into the system image anymore for each port, but differences are resolved in overlays that get put on top before the libc container actually starts. We also have binderized HALs here, and that one is the one I wanted to mention earlier, binder IPC. So it is an in-kernel IPC mechanism which provides multiple contexts in /dev. So we have different files that you might want to open and communicate over. We have one for the Android framework or our stub services. We have one for hardware services, and others for the vendor are provided by the VND binder context. Previously, there was a debate, just as a side note, there used to be a debate about dbus over binder from the systemd guys and Leonard Puttering specifically, but those discussions stopped because it was inherently different in the threading model between dbus and what Android usually does with its threading pool and accessing those from a thread pool. Then hardware support. We have a bunch of different examples here of how rootfs components on the left versus Halium components on the right are communicating. We have PulseAudio, which is providing a HAL solution in process, and SensorFW, Reparty, Ophono, location services, they talk to Halium side HALs over binder to provide what we want to provide. We also have Network Manager as an example here, where Network Manager is handling Wi-Fi itself using regular facilities that you're used to from mainline Linux. And we've also, as a side note again, deprecated platform API that you might know from Unity 8 times. And GPS is the only remaining consumer, minus the code drop, which has not completely happened yet. But yeah. So Halium overlays, I'm just going to go through this real quick. We have different configurations for PulseAudio, for maybe Ophono, for telephony, for different things that make the device actually usable, and those are provided over Halium overlays. They're part of the device tarball that gets fetched per port, per device, and it applies the overlays at runtime using either overlay.fs or bind mounts again, and we pull those from UBport's system image. And a true device integration for an Android device needs this, because we can't, for the foreseeable future at least, make the software auto-detect everything, all the properties that are making the software work on this particular hardware versus another one. Different Halium generations, a different number of SIM slots per device, etc. Those need to be configured sometimes and very often. And this makes it very hard to make a unified approach here. Next, libhybris, the thing that actually allows a bunch of things like graphics to work. It's basically the Android library loader built as a glibc library, provides glibc wrappers for libgl and OpenGLES and whatnot. For Wayland specifically, it shoves in a Wayland listener to handle the Android buffer passing, and it also talks over a socket to the property service inside of Halium to tell it, hey, wait a second, which Android version are you again? Oh, you're Android 9. OK, I'm going to use that linker. And then it does the linking on the other side. It resolves the symbols with the correct linker and provides the results when the functions are called. So as used in the wild, again, we load the libraries into the glibc process, resolve the glibc symbols for bionic equivalents, optionally set up some hooks for redirection in case there's a requirement for that, and do the bionic function call in the back when the glibc function gets called and returns the values that it needs to return. There are also compatibility layers, which allow us to access multimedia and camera, and also graphics, particularly not only OpenGL graphics through Android graphics buffers. So in the old way, this used to be Mir Client handled. Mir Client used to have a separate integration for Android devices, and libhybris driver userspace gets loaded, the linker sets up everything, Mir Client Android client implementation gets loaded, and then Android EGL initializes in the back. With the new way, we instead have Wayland EGL load the EGL implementation of libhybris, and then we set up the buffer passing on the active socket so that Android buffers are actually passed along without the client to require any modifications, and then Android EGL initializes instead after that. Another very particularly annoying topic is the TLS padding hack, because now we have two C implementations loaded into the same process. Those two might not have the same idea about what to do with thread local storage, how it is sized and whatnot. So we have one particular issue with one particular device, with a particular Halium generation, where the graphics drivers are statically linked with bionic, and we can't just do the change on the bionic side and say, make the TLS slot this much and this big and that many and stuff like that. Actually, what we have to do is LD preloads, and thanks again to Rachanan over there, who came up with this beautiful hack. It basically sets up the process to have padding in thread local storage every time a thread gets constructed using an LD preload hack. So this is the content of it. It's just allocating 16 bytes, 16 like void pointers, and calls it a day with just providing the space requirements so that glibc and bionic don't trip over each other. So snapd changes. Kernel adaptations for snap support, again, we need AppArmor, we need SquashFS, we need cgroup v2 enablement for many things so that device access can actually be checked. And this is a burden on the device maintainer's side. So the device maintainer needs to provide a working kernel with all those features enabled and tested so that we can ensure that Ubuntu Touch has snaps running properly. Yeah, snapd changes also include some particular necessities in the rootfs, handling a different rootfs, because it is not a classic system, but also not a snap-only system. It's a hybrid in between. So we have a read-only rootfs, which looks similarly enough to a classic one, but we also have the /system symlink, the /vendor symlink to /Android, and also we need, for particular use cases, we need extra uses to be used similarly to Ubuntu Core. So we just, in our variant of snapd, in our fork, with our custom patches, we just tell the system in snapd to ensure that it checks whether this is Ubuntu Touch or not. And if it's Ubuntu Touch, it enables the extra users use case instead of writing to /etc/group, etc. And we also do libhybris environment setup through environment variables and passing those files and mount points that are required into the environment in snapd confine, or snapd and snap confine. So integration changes for Ubuntu Touch apps to shine in the Snap Store for Ubuntu Touch specifically requires Content Hub, Media Hub, Download Manager, online accounts, and a bunch of other services to work properly. Some of them already have a work-in-progress patch set on my local laptop. That's just adapting the change from Unity 8 to Lumiri so that the dbus interfaces are allowed through the App Armor profile. And we also have Content Hub, which is a way of passing content and files and data around between processes, or between programs actually, because those programs get started as needed when you select them. And that also includes that Snapd would have to generate some metadata for Content Hub to actually know which application does provide which content functionality, so that we can start it and ask it, please give me this file if you're the gallery, please give me this QR code if you're the QR code reader, etc. Right now it's completely disconnected. You can't just ask around whether there is an application that is supported for a particular document type or content type. So that's that. Now, the all-snap deal, just to finish this off real quick. So we have seen a few reasons why this all-snap idea for an Android-based device would be harder to pull off than on mainline. We have the vendor blobs, which are not very often redistributable at all. And again, we rely on a pre-installed, very specific Android version providing the blobs for us to ship all free and open source software. We need /Android, so the Android rootfs, plus a few symlinks in the Snap runtime environment. We have seen a few challenges with the Initramfs situation in early boot. Snapd and gadget snaps are right now not capable of handling the setup for Android bootloaders to actually provide a bootable image. It's just not there yet. And Google dictates, this is the most important one in my opinion, Google dictates the partition layout, not you or me. And we are bound to what the vendors of the devices set up for us to provide a bootable, workable system. And still old Android kernels, which we've learned to live with. So my personal idea here has been for some time now, create Snapium. Just Halium, Ubuntu Core, now Kiss. And the idea would be to just do all the setup of the environment for mounting the right partitions, setting up the super partition, and doing everything that is required so that Ubuntu Core doesn't have to care about it, a step before that. And the initial mindset is, because it is a proof of concept, or a planned to be a proof of concept, it might never truly be Ubuntu Core, but at least we can try. And in case you want to see this happening, Army, let's get shot done. And if you want to read up on all the topics that we have heard of right this moment, take a look at these resources. There's also my personal address at the bottom. And yeah, if you have any question, if we even have time for a question, 1.5 minutes.
Aside from everything else we talked about, I just noticed you had extra users there. We probably don't need it. There are ways to, in Snapd, to make use of its own user management.
Okay. Yeah. Okay.
We can talk about it.
Yeah. Let's talk about it later.